Welcome to WSKG Science Pub, a monthly series exploring the dynamic and exciting scientific world around us. I'm your host, Nancy Scales Coddington. We are going to dive deep, very deep, during the next hour. Geothermal is something not often considered in the Northeast due to the depth required to find heat. We as a society face the challenges of weaning off of fossil fuels and switching to sources that do not add greenhouse gases to the atmosphere. Electricity production from alternate energy sources like wind and solar can help, but what can be done to replace over 30% of New York State's energy consumption that is used to heat our homes and offices? Cornell University researchers and staff may have that answer. They are exploring how the heat deep below our feet, geothermal energy, can fill this need. This past summer, a 10,000-foot deep geothermal observation borehole was installed on the Cornell University campus, and we are going to talk to the experts who've been working on this project for several years. Joining me is geologist Terry Jordan, recently retired from nearly 40 years of teaching at Cornell. Yet she continues as a researcher examining the use of sedimentary rock distributions and properties to reconstruct Earth history and to provide natural resources. For the last decade, her focus has been to discover the history of millions of years of climate change and water availability in the Atacama Desert of Chile, and to help find more environmentally benign ways to meet society's needs for energy using underground resources. Her primary ongoing project is geothermal energy exploration in Eastern North America, with a focus on the Cornell University Borehole Observatory. Welcome, Terry.
Thank you.
Bert Bland is a licensed professional engineer and is responsible for operating the district energy system that generates heat and electricity for 250 major buildings on Cornell's Ithaca campus. That is no small job. He is also responsible for transforming that energy system to achieve a carbon neutral campus by 2035. Bert served as the executive director for the construction of the Cornell University Borehole Observatory. Welcome, Bert.
Thank you, Nancy.
Don Haas is the director of teaching programs at the Paleontological Research Institution and its Museum of the Earth and Cayuga Nature Center in Ithaca, New York. He is nationally regarded expert in climate and energy education, place-based and technology-rich earth and environmental science education. He is co-author of the books The Teacher-Friendly Guide to Climate Change and The Science Beneath the Surface, a very short guide to the Marcellus Shale. Welcome, Don.
Thank you, Nancy. It's a pleasure to be here.
Well, we are very excited. We have some really wonderful experts with us this evening, and we are glad you're joining us as well. We are going to take a quick look back over the summer and the installation of the Cornell University Borehole Observatory, or CUBO. So let's take a look.
Transitioning away from fossil fuel-based energy sources can help reduce the impact of climate change. When we change our energy source, we change history.
The future of energy worldwide needs to be without carbon in the energy source. There are limited choices of how to get energy, but one of them that's distributed everywhere that people live is to go underground to where the rocks are hot.
We have almost infinite energy right below our feet pretty much everywhere in the world. It's available 24/7 all the time. And if we can just figure out how to use it efficiently, it really solves our energy problems in ways that other renewable sources don't.
This is Kubo behind us. So in its condition right now, it allows us to make it into a long-term observatory. In those different ports and valves and everything, we can put scientific instruments down inside of the well. We've been able to characterize the deep ground underneath here that is representative of much of New York State and much of the Northeast. We did a lot of testing of the borehole, of that open section between 8,000 feet to 10,000 feet deep. And we could see in there fractures, particularly in these zones that we think might be potential reservoirs. That's really good because those fractures could be the places where we allow fluids to flow in from one well to the other well and absorb a lot of heat. We have lots of data now, and lots of attention needs to be brought to that data to kind of figure out, so what's next? Already Kubo has been a great success. It's a success in that all of our students, like Roberto and others, are learning how to do this and how to essentially be the leaders that develop this and do geothermal energy throughout the United States and throughout the world.
So Don, can you talk a little bit about, how did we actually get to this point? What is the problem we're trying to solve? And tell us a little bit about the background.
So the problem we're trying to solve is climate change, and basically we need to stop burning so much. Fire has fueled human civilization since the dawn of civilization, and that has made it society possible. But now we need to get away from fire, and this smaller scale effort to move from heating the Cornell campus with natural gas from its combined heat and power plant to heating it with a carbon-free source is a small step in a larger effort, and a very important first step. We are striving to make Cornell carbon neutral by 2035. Heating the campus is responsible for about 40% of Cornell's emissions. And not only are we trying to do this for Cornell, but Cornell is trying to be an example for others. If we can make this work in Ithaca, New York, where there's nothing particularly special about the geology below the surface, then it can work pretty much anywhere. And I'm going to try and make the point about carbon emissions by talking a little bit about burning stuff. And natural gas is hard to wrap your head around because it's an invisible gas and we don't really see it. So I'm going to talk about gasoline instead of natural gas. And I've got a chunk of graphite here, which is pure carbon. And I want you to think about how this amount of pure carbon compares to the amount of carbon in a gallon of gasoline. So put that thought in your brain. There's a picture of that same piece of graphite. And I'll note while we're looking at that Americans burned about 369 million gallons of gasoline per day in 2021, more than a gallon per person per day. And now I want you to take a look at the chemistry by looking at a little animation of the burning of octane, the main ingredient in gasoline. So can we run that animation? Now, here we go. So we're going to look at a cartoon of the combustion reaction of octane, the main ingredient in gasoline. And that's a chemical reaction that combines the octane with oxygen from the atmosphere. And we're going to give that octane and oxygen a spark, and things recombine. So now we've got carbon dioxide and water vapor from the octane and the oxygen that we started with. And there are our carbon dioxide molecules and our water molecules. And when we look at what we ended up with, which will come up in a moment here, those 8 carbon dioxide molecules weigh a whole bunch more than the octane molecule that we started with. And that's not magic, it's chemistry. It's we end up with starting with a 6-pound gallon of gasoline and burning it and ending up with 19 pounds of carbon dioxide because it's pulling oxygen out of the air. And we do that 369 million times a day in the United States. And each one of those gallons of gasoline that we burn puts 3 times this much carbon into the atmosphere. So 3 times that block, 5.5 pounds of carbon goes out your tailpipe for every gallon of gasoline you burn. And we've got similar chemistry for burning natural gas. And you can, try and picture those blocks of carbon being put out of your tailpipe, which of course is not exactly what's happening, but it is that much carbon. And understanding the scale of things is profoundly important for having a really deep understanding of the nature of climate change and the energy issues we're talking about. So we need to figure out how to stop burning. I was there for a moment. Take a second.
So, Don, you're talking about gasoline, but why would we need to change the way that we heat, our buildings or our food? Why shouldn't I continue to use wood when I'm cooking my steak or natural gas to heat up my water for my tea?
Yeah, well, the chemistry is pretty similar for any combustion reaction. It's just pumping out carbon into the atmosphere. And the transportation fuels like gasoline are about 1/4 of US emissions. And like I said, about 40% of Cornell's emissions is coming from burning natural gas for heating buildings. So we've got to figure out how to move away from fire. And ultimately right now, something like 80% of global energy is from burning stuff. And as I said earlier, fire has powered society all the way along, and that's made modern society possible, but it also now endangers modern society and has actually been endangering it for some time now. So figuring out how to get away from fire is really crucial. And one of the things to realize in that process is that natural gas, for example, burns at a temperature of about 3,600 degrees Fahrenheit or 2,000 degrees Celsius. And that's way hotter than what we need to do for most of the things that we need to do in our homes and businesses. So if we can figure out how to get stuff that's hot enough to do the trick, but not way more heat than we need, then we can scale this up. So for heating buildings, what we need is something like 80 degrees as a maximum for the air coming out of your ductwork, or for the radiators in a building, which is how Cornell is heated, is with radiators. That water inside the radiators needs to be, depending on the technologies, somewhere between 130 and 180 degrees Fahrenheit. And like I said, the natural gas flame is about 3,600 degrees Fahrenheit. So figuring out how to use hot, but not so ridiculously hot energy sources is a fundamental change in our technologies. And again, scale is hugely important. And, thinking about, well, why don't we just use geothermal heat pumps or ground source heat pumps for doing this job? Well, the average New York home is about 1,500 square feet. And the amount of heated square footage of building on the Cornell campus is about 15 million square feet. So that means we need to have 10,000 home-sized systems set up on the Cornell campus. And obviously that's just not doable. Those geothermal systems are great. We can take a look at the basic kinds of ground source heat pumps. Got a little diagram that shows the 4 of the common types of ground source heat pumps or geothermal heat systems for homes. If you want to put that image up, there we are. So that's what a home source heat or a home scale heat system can look like. And like I said, the size of the buildings heated on the Cornell campus is 10,000 times the size of the average home. So we really can't practically do that on the Cornell University campus. So we're going really deep instead of those comparatively shallow systems for homes. And I think I'm going to pass it off to Terry.
Yes, that was a great background to give us on why we need to start transitioning and looking at other ways to heat. So, Terry, can you explain what is deep geothermal heat?
Yes, I do think there's a diagram to go along with this one also. Yes, so the interior of the Earth, this is a pi wedge whose bottom point is the middle of the Earth. It's about 6,000 degrees Celsius or 11,000 degrees Fahrenheit. And us up here on the surface are at somewhere, today we're close to 0 degrees Celsius, right? So heat always moves from where it's hot to where it's cold. So heat is everywhere around Earth, moving outward or from that center out to the Earth's surface. And so there's a resource. Heat is coming to us from below us. Today, that heat is used to generate electricity, geothermal electricity, but only at geologically really special places, usually close to volcanoes, for instance. And so none of you watching even live somewhere near where geothermal electricity is created. But that means that all the rest of the continental areas where almost all of us live, we're sort of wasting this heat that's moving out from the center of the Earth, and we could see it as a resource offering itself to us for use. That would be great. That would help convert us from burning things to having another source of heat. But the technical challenges of like harvesting that heat from widely around us underground is a technical challenge. We have to figure out how to harvest it. Essentially, we need to use water to take on the heat, and then the heat from the water transfer it to us. This is a technical challenge. It's not easy to do. And so the Department of Energy has been very interested in geothermal energy. They've funded Cornell's faculty and students for about a dozen years to try to advance understanding of what are the opportunities to use this heat more widely. But just this year, they actually really announced a whole new program. This is the Department of Energy that is sort of a moonshot for overcoming the technical problems that are keeping us from using this geothermal heat everywhere. And they call this enhanced geothermal systems. Anything that would succeed would fall under that label of enhanced geothermal systems. So what Cornell is doing or attempting to do falls well within this Department of Energy sort of priority of trying to utilize widely this available heat.
Thank you. That really helps to give us a bigger picture of what is actually happening. Bert, can you talk to me about how is this different from the geothermal wells that I could have installed at my house?
Right. Okay. So here's a good example of a heat pump. And this is what normal commercial, industrial, or residential electric heating works on, whether it be ground source or air source. According to the second law of thermodynamics, heat energy does not flow from cold to hot. So if you want to get heat out of the ground where it's ambient, like 55 Fahrenheit for a ground source heat pump, or out of the air where it's like today, 20 degrees or so, you have to put energy into the system to get the heat energy to flow from that type of temperature, 55 or less, to a temperature much higher to heat the space. Now, as Andy said, you want to heat a space, let's say to 68, 70 degrees. You still need to bump the distribution in the building up to like 120 Fahrenheit, 130 minimum. Our buildings use 180. So a heat pump uses electricity. That's the compressor at the top takes a motor input. Basically what's happening is the ground energy is boiling the refrigerant, that's the fluid within the heat pump, boiling it, taking heat away from the ground loop, compressing it, condensing it on the condenser side, giving up the heat to the loop within the distribution system in the building, and then it flows around and around, boiling, condensing, et cetera, with the compressor running, taking electricity. Now, these are a perfectly great way to heat commercial, industrial, residential buildings. We are going to, as Don said, we're going to stop burning stuff. We're going to electrify heating as we are electrifying transportation. But when you have a district energy system like Cornell's, where we distribute central distribution to 250 major buildings, you have the opportunity to bypass the heat pump, bypass the use of electricity, and go, as Terry described, to deep direct use, in our case, 3 kilometers down, where it's 180 Fahrenheit or so, and hot enough to heat the buildings without the heat pump. And why that's important, I think we'll talk about a little later, because it's if we were to go to heat pump system, we'd need 10,000 wells, shallow wells, and we'd almost double our electric use in the winter using heat pumps. So we're trying this to demonstrate deep direct use without that electric load from heat pumps.
Yeah, it seemed you would be kind of negating some of the work that you were doing there by doing that, right? So Bert, you have the very lofty charge that Cornell is going carbon neutral by 2035.
Right.
Yes. How are you going to do that?
Well, here's our iconic visual on how we're going to do that. Basically, starting from the left, which is about electricity, we're going to, now our electricity is largely made through natural gas combustion in an efficient combined heat and power plant. We're making using the waste heat, but we're going to convert to all water, wind, and solar. And the way we're going to do that is we have a hydro plant, a relatively large hydro plant built in 1904 in our Fall Creek Gorge, 1.5 megawatts, which is about 5% of our need that it fulfills. We have solar panels on rooftops. All our new buildings are going on with rooftops, but that's not enough area. So we have solar farms on Cornell property outside of our campus, 28 megawatts production. So on a sunny day, those solar farms will create, at high noon, will create the amount of electricity the campus is using. But on an annual basis, because it's not always high noon, sun's not always shining, it's about 20% of our energy that there are solar farms. So we're going to continue to build solar farms on campus and off campus, and rely on the grid. Actually, New York State has very ambitious plans to decarbonize the grid. So New York State's goal for 2040 is to have a carbon neutral grid, all made by nuclear is included in that, nuclear, hydro, wind, and solar. So yeah, there's the future. And the future of heating is deep direct use earth source heat. So here's how it works. The yellow straw on the left is the borehole we just drilled to 9,790 feet, the borehole observatory. Always will be for data gathering. So we're trying to, that goes through, I think maybe Terry will talk more about this, but that goes through about 9,000 feet of sedimentary rock and into the crystalline basement. And we're identifying target formations for the production well pair you see on the right, The idea is we put down water, release it into the target formation, a distributed fracture network with a lot of surface area where it picks up the heat and comes up the red well, which is the production well, and then is circulated to campus where we have converted from steam to hot water. And that's right now we've only got the first borehole observatory, and we're studying how to design the production well pair to demonstrate the deep direct use of earth source heat.
Thank you, Bert. So yes, I think we are going to jump back over to Terry to guide us through talking about what is the Earth Source Heat Project, which you think that that's very easy to say, but it's not.
So if we were to go to the diagram we were just looking at, the sort of multicolored block, yeah, that one. So Earth source heat is the vision for capturing the heat that naturally is underground, harvesting it using water as the farm vehicle that harvests the heat, and bringing it to the surface and then transferring the heat through heat exchangers into clean water. I'm going to call the underground water dirty, which just because it's really full of salt, not because it's muddy. So we want to separate the water which carries the heat from underground, set it back underground, and just transfer the heat to sort of normal surface water and put that into the system of pipes, which Cornell already has, carrying heat throughout campus. And that is what that two-part system sort of is the vision that Cornell calls Earth Source Heat. Today, we have the existing district energy system, as Bert mentioned, pipes underground, they carry heat. But today, the heat comes from the combined heat and power plant, burning gas to create hot water. And the piping system would be just as happy if it carried water that had been heated from underground heat. So Earth source heat is the change of the system of where you get the heat from burning something, which Dawn has said is bad, to just using what nature is sending past us all the time, if only we were catching it. So what we have, Bert has shown you that there is adjacent to this future set of wells. What you're seeing here is a future set. We didn't know enough to be able to go ahead and just do this. The diagram is kind of nice. It shows layers of rocks of different colors. It shows us some rocks at the bottom below 3,000 meters depth, which are blobby. We don't know too much about them. And it shows us that we had good estimates of what the temperature is. Over on the right-hand side is a temperature scale in degrees Celsius. It says 40, 60, 80, and 100. This was a pretty well-constrained estimate because New York State has archived 100 and some years of previous deep wells that were drilled for oil and gas exploration. We had data about what temperatures we might expect. So it isn't too much of a stretch of the imagination to draw a block diagram like this, but what we really, which shows rocks and estimates how deep do you have to go to get heat. But what we knew nothing about was really what was the capacity of those rocks to transmit water. And if water is going to be what we use to harvest heat, we need to know whether the rocks will transmit the water and how close the natural situation is to permitting that to happen.
Thank you, Terry. We did have a question. How is the collection layer fractured to allow fluid to flow in there?
So the collection, yeah, I think by collection layer, I'm pretty sure you mean what I would call the reservoir. So rocks are naturally fractured. And perhaps later we'll look at some figures that show you some illustrations of naturally fractured rocks. If you live somewhere here in central New York, you've been to the gorges, and you probably have noticed that there are the horizontal kind of planar features, and there's a bunch of vertical fractures in the gorge walls. Well, I just use the word fractures. There are these lines in the gorge walls, and that it's along these natural fractures and bedding surfaces that the plants take root, and clearly there's water seeping out. And here in midwinter, we'll see icicles forming along these fractures. That's because naturally the rocks have fractures and water can be transmitted along the fractures. So what we are looking for, to more directly answer the question, what we needed to know was if there are horizons already present or depths already present, which have natural fractures, which have some capacity to transmit fluids, and how much capacity is that to transmit fluids. There may be, as part of this Department of Energy Enhanced Geothermal Technology program is focused on, there may be a need to help adapt to the natural fractures to actually be interconnected and allow the water to move long enough distance to be of use to us. But we're very much going over what already exists for fractures.
That's great. Thank you so much for that. I think we're going to shift over to Bert, and I want to ask, how does the Earth Source Heat Project, serve the state and the broader world?
Well, as Terry said earlier, we can show geothermal energy working not just in tectonically active areas like Iceland or the Ring of Fire in the Pacific, but in normal geology. Now, New York State, so this is a us energy nerds really like this graph. I'm going to take a little bit to walk through it. This comes from the New York State's Climate Action Council working group meetings, predicting 2050, the energy use. So in the vertical column on the left, where you see gigawatts, you see it's 40 running up to 50. Right now, we peak at about 30. So what that shows is the electric demand in New York State is going to increase because of electrification of transportation and the electrification of heat, as it should. But that's a challenge to produce that carbon-free. So what we have here is 7 days, what's called the dark doldrums. The Germans call them Dunkelflaute, meaning the sun is not shining much, it's gray, and the wind is not blowing. So I'm going to start the stack from the bottom. The first at the bottom is the nuclear power. We have 3 nuclear plants in upstate New York. We have carbon-free. We have 2 large hydro plants on the St. Lawrence River in Niagara Falls. And then we can import power. So that shows kind of a base load. The 2 blue is, the dark blue is onshore wind farms, and the light blue is offshore wind farms that are just starting to be built. The first one's being built right now off the South Fork of Long Island. The yellow is a sunny day, and you can see how it's periodic when the sun's shining. The purple is the use of batteries. So, and you can see in day 7, it looks like the offshore wind finally picks up in this scenario. But the challenge here is the gray, is the balance of power needed to meet the projected demand. And right now, it's just a need, and it's unidentified how that need will be filled. So I think that's what I want to show here, but I'd just like to say, so we will electrify heat. Cornell will do that, but we're trying to avoid the high electric demand from heat pumps by the deep direct use of electricity, so that we don't contribute to that gap of what we think will be produced carbon-free and what we need in the year 2040, 2050 So if we can show that, it's not only good for Cornell, it's good for New York State and the region, any cold climate region.
Bert, is Cornell ready to begin conversion to geothermal heat?
Good question. That's kind of a two-part answer. One is we have to convert from steam, which is made by, as Don mentioned, 3,000 degrees Fahrenheit combustion of gas, which we do now. So we're starting to convert for our distribution system to heat. New buildings are low temperature, served by hot water. But that will happen, but we are not ready to heat the campus with the deep direct use of earth source heat, because right now we just have one well in the ground, and it's an observation well. So we have several years to go. We hope to get funding from the Department of Energy, perhaps from New York State Energy Research and Development Authority, to help us demonstrate the first well pair, demonstrate the actual deep direct use of heat and serve our campus, a portion of our campus, with the earth source heat production of hot water. So right now we're not ready. We're getting ready, and we're doing a lot of studying, as Terry mentioned, of the target formations down there at the heat. So we know we have the heat, and now the challenge is how do we get the flow, and then how do we get it to the surface.
Thank you. So Terry, what was known before the borehole was actually drilled in order to plan this well?
I mentioned that New York State, as most states, have been archiving data. There's tens of thousands of old oil and gas exploration wells, there were none right in Ithaca, but the townships around us, there were other ones. And because the state Department of Environmental Conservation archives the data, that means we can tap into what had already been determined in previous gas exploration projects. Most of that data told us about what composition of rock, the solid rock, we would find at what depth. And it wasn't too hard to find out what's to the east, west, north, and south of Cornell and project it underneath. That's how we established this diagram of the colored layers of sedimentary rocks. And the state also uses the knowledge from the nearby boreholes in order for them to set their regulations of what do we have to do in the borehole at this depth and at that depth, and when you find this formation and that formation, in order for the borehole itself to be safe, to avoid explosions, to avoid collapses of the borehole. And the state uses all that prior experience to establish its regulations that they apply to us. So we benefited from all the prior knowledge. But we knew almost nothing but from all that prior data, we had almost no knowledge of what were the waters, where would we find deep water, where would we find fractured rock. So we could draw nice diagrams like this, but we really could not answer the question of what horizon, what depth zone should be targeted in order to extract the geothermal heat.
Yeah, it's nice when it's this labeled out, right? It looks very clean and neat.
Oh, doesn't it? Yes, yes.
Bert, can you walk us through the drilling process and talk a little bit more of how that process worked?
Yes, it was fascinating. So we tapped into the drilling industry, the oil and gas drilling industry, who I think is more than willing to pivot from drilling for oil and gas and exploring and producing oil and gas to geothermal. So basically all over the Appalachian Basin, Pennsylvania, West Virginia, and Ohio, there's drilling for natural gas from Marcellus Shale and from Utica Shale. So we contracted, we were called the operator, which is kind of a term of art in the business. So we were the general contractor to make this happen. And we contracted first for a drill rig. Drill rig came up from Pennsylvania, huge piece of equipment, coming in 70 tractor trailer loads, 70. There it is. Uses a lot of electricity. The good news is most throughout the Appalachian Basin, a lot of the drilling is happening far from good power sources and good distribution lines. So they rely on diesel generators. Because we have a grid, a microgrid, we were able to supply our own electricity through a transformer. So we didn't have the 24/7 noise or the 24/7 pollution from a diesel generator. That was a nice feature of our site here. The drill rig shows up, and they basically show up with a drive shaft, and the operator, us, has to contract for just about everything else, including the drill bits. So we had to contract for drill bits, drilling fluid, known as mud, which lubricates the drill bit and brings back the cuttings, pieces of rocks to be separated. So the casing, we cased 2/3 of the hole off. And the operation runs 24/7. So the drillers, there's a crew of about 6 drillers working for their drill rig, and they go 12 on, 12 off. They go 3 weeks in a row, then they go home for 3 weeks. But basically, it was a 24/7 operation, no break for Memorial Day, no break for Juneteenth, July 4th. Went 24/7 from the mid-June through the end of August. Quite intense. Not problem-free. Things would break, and when they break down whole, you have to go fishing for them with the fishing tools that grab onto the broken tool and bring it back up. As Patrick mentioned, Professor Patrick Fulton mentioned in the video, we were able to get 7 students covering a 24/7, one person 24/7, shared by 7 students, sample catching and helping analyze the cuttings that came up to find out what geologic formation we were in. So basically, we had 24/7 coverage between mud engineers and drill loggers. We pretty much had 10 to 12 people there around the clock, with more when cementing was happening or special operations. So first time I personally had been involved in a drilling operation, found it very fascinating. Can't wait to do it again.
It was very impressive, and it was really quiet as well.
Yeah, right.
I'm going to toss this question over to you, Bert, but Terry, do please jump in if you would like to. We have a couple questions. One is looking at a system that has a vertical deep well using a pipe within a pipe. So sending cold water down the inner pipe while channeling warm water back to on the outside back up to the surface. You are going to lose a little bit with that surface area, but you would only need to sink a single well. So would something like that be feasible?
So that's called a closed loop system. In fact, there are attempts to commercialize that. And it's got some advantages. You don't have to find or create a distributed fracture network, but it's really not enough surface area to get the heat transfer out of the rock into the fluid that we want to produce up hole. So yeah, we have looked at it. In fact, our principal investigators in the College of Engineering have studied that. It's not really technically feasible or economically feasible just because of the lack of surface area by putting, basically it's sort of a closed loop or piped radiator down at the bottom. So no, it's not something we think is technically or economically feasible.
Thank you. That's great. All right, I'm going to switch back over to Terry. And we do have a question. One of the diagrams that we had up, we have the lake there as a heat exchange. So that is actually currently happening with cooling Cornell University. Does that actually alter the temperature of the lake?
No. So yes, it's in the diagram. It's been very good at helping. It's not that diagram, but it's very good at helping Cornell to prevent having the increase in energy use through the years. Bert could, that's it, yes. Bert could tell you how much it has saved in environmental and cost, I'm sure. But no, so the water itself that comes out of the lake, you see it going into that little building. It goes into that little building. It exchanges its coolness, its heat, with water in a separate loop that goes up to campus. And it only has to exchange off a little tiny bit of its, there's a little tiny bit of temperature differential before the lake water goes back into the lake. And it goes, so I'm sure Bert will, I think it's a couple degrees Fahrenheit difference between what comes out and what goes up. But it has essentially given the university a great deal of confidence that, oh, if we can get a hot water stream coming out of the ground from the future Earth source heat, we know how to exchange its heat and make this part work to distribute it on campus. So it's sort of like developed quite a lot of technical expertise. And let me add to what Bert had just answered about the closed loop system. We had one of our industrial collaborators last week comment, and I'm never great remembering numbers, but I think he said you need something, a 30-mile long pipe of that pipe inside pipe system to bring up the amount of heat that Cornell needs. So I don't think anyone's going to drill a 30-mile long well. So
yeah, that is pretty long indeed. Terry, while drilling through the bedrock, what did you find that advances Cornell's evaluation of Earth source heat?
I'm going to split your question into two parts. You said during drilling, and we did learn things during drilling, but what is now advancing our ability to evaluate Earth source heat is really what happened when drilling got done. So while we were drilling, the fluid that was sent down into the borehole to lubricate the bit brought back up to the surface the ground up pieces of rock. Think of if you're drilling into a piece of wood, you have sawdust created. Well, broken up pieces of rock were created by the drill bit. They had to come up to the surface. We examined those, and they were the reality check on, did we really, as we went deeper and deeper, find the rocks we had predicted we would at the depths we said we would. More or less, but not always perfect. And so I think there's a diagram of the drilling progress through the calendar, if that could be brought up. But so as we went down, we had to continually be making decisions about, have we reached the point yet where we need to install one of these steel and concrete casings, or aren't we there yet? So these rock chips are coming up are the way to take the pulse on our progress. And we had to know that because the state regulations say at such and such a unit is when you have to stop and put it in a casing. And so we had to know if we were there or not. And so in this progress of drilling, you see we go deeper and deeper and deeper for 4 or 5 days, and then we don't go deeper. That's because that's when the casing and cementing was going on, and then we could start drilling. And so we progressed like that. This is about 2 months of drilling, and it wasn't until about the last 5 days that 7 days, I don't remember exactly, that we got into beginning to have data available, which was giving us insight into whether the rocks would transmit the fluids. We're naturally transmitting any fluids. So in that last span of drilling that starts around the start of August. Then we had an extra monitor in the borehole. We weren't just getting the little rock chips. We're also had a spectrometer which was detecting very minute amounts of noble gases and inorganic gases. Yes, that's it. And here you see on the left-hand side are the layers of rocks we were going through. And on the right was how much was the record of helium coming out in the drilling mud, and argon gas and hydrogen gas. And there's really no reason for rocks down there to have helium, argon, or hydrogen, but there's minute amounts of all of these gases in Earth, and they all rise. They're all very buoyant gases. They're trying to get out of the solid rock. And so depths at which there were anomalously large amounts of helium, for instance, you can see several places where the dark blue helium spikes in amount. That's a sign that, my gosh, there must be interconnected flow paths in the rock, which means that all the helium that was around that area is collected there, waiting for us to drill through it so it could pop out. So that's telling us that is an interesting interval for possibly having water capacity to flow water through it. And there's some other depths where that happened. So that was exciting. But then, as soon as we finished drilling, the other thing we learned in that bottom part was that actually we could drill it fairly fast. There had been a concern that we might just be creeping along at a couple of feet a day, and we would run out of money before we ever were able to drill through that. But it wasn't true. We were drilling through it quite well, which is encouraging, because if there's going to be reservoirs, we need to go back. So, but in that last week, could you go ahead to the next diagram? We started to be able to do that. We drilled all the way to the bottom. No, that was a beautiful one. Step back, please. And then we could put tools into the borehole to collect data. And the way you put the tool in is with this big spool of wire full of electronics that you would reel in with the tools on it, or reel the tool back out and put on a different one. And now if you go forward, this is one of the most exciting, this is the truck that the wireline tool is coming out of, is the bright blue one over on the right-hand side. But if you go to the diagram that you had up a minute ago, it's sort of bright orange. Yes, okay. One of those tools was giving us sort of like sonograms of the inside of the borehole. So the picture on the right is what we see of the borehole wall in a 10-foot distance. And it sure looks a lot like the photo of the rocks at Ausable Chasm over in the Northeast, because we're seeing layers. And so now in the data sets we got here at the end, we advanced from the point of having little ground up bits of quartz, feldspar, various minerals, to actually seeing how they were constructed together as rocks. So I know we're nearing the end of the time. I want to emphasize that now that we can see the rocks, now that we have, from all these tools that went into the borehole, we have measures of their resistivity and density and hydrogen content and potassium content and all of this. We now really can be much better describe what are those rocks made of. We can see with various means of seeing where there are fractures in those rocks. We can see some of the fractures have the capacity to transmit fluids. This is a photo of what a naturally fractured rock from the metamorphic basement looks like. And we're seeing things like this in the borehole image logs. So now we can target horizons at depth which have combinations of properties which look promising for transmitting fluids. And that's really what we were looking for. All of this new knowledge now really gets handed forward to people who we might call reservoir engineers or completion engineers, for them to estimate really the feasibility of going back in with the injection well and a production well and causing hot water to be transferred between the two wells so that it can be brought up to the surface. So the Kubo well gathered data, and we're currently very busy analyzing data, but that was as a data gathering exercise, it was great.
And how much more data do you, I mean, it sounds like you really could just continue collecting data for years and years and years and years.
Well, it is an observatory well. There will be installed in it some permanent sensors that will allow not only, sort of passive monitoring of data, but if we go ahead and put in the demonstration wells, the next ones that Bert has talked about, then we have an ear on the rocks right down there at the depth where the work would be going on in the new boreholes, so we can monitor and, if there's problems detected and change actions or simply better understand how water flows through the system.
Thank you very much. Bert, how many wells do you think we would actually need to run Cornell campus?
So I hesitate to answer that. Not enough data to answer that question. It really depends on the distributed fracture network that we find and can create and what kind of flow we get. Perhaps 3 well pairs, 5 well pairs would be a really sort of economic amount, economically viable. But again, too soon to say, Nancy.
And if we wanted to find out more information about all of this, where can we go?
Oh, so there's really 2 good websites. And can you put them up? I think
Absolutely.
Earth Source Heat at .cornell.edu. And there's another one, the Deep Geothermal research site. They're very deep and excellent sites. Maybe you can put the links up.
We will pop those into the chat so that everyone can go and find out more information about everything that we talked about tonight. I know it was a quick hour. I would like to thank our guest, Terry Jordan, the Department of Earth and Atmospheric Sciences at Cornell University, Bert Bland, Cornell Facilities and Campus Services, Don Haas, the Paleontological Research Institution and its Museum of the Earth and Cayuga Nature Center. Thank you so much for being here with us tonight.
Thank you, Nancy. Thank you all for attending.
Yes, thanks. Thanks to all.
You can watch past WSKG Science Pub through the PBS app, on demand on your smart device, and on WSKG's YouTube channel. Be sure to like our Facebook page for future events and science updates. I would like to thank Cornell University, the Paleontological Research Institution and its Museum of the Earth, our WSKG team tonight, Andy Piak, Alyssa Micha, and Patrick Holmes. Support for Science Pub is provided by the Robert F. Schuman Foundation and from viewers like you. I'm your host, Nancy Scales Coddington. Thank you for joining us.